The second phase of ethical hacking is scanning, which helps develop a profile of the target. In this segment, we'll learn how scanning helps discover responding hosts, check for listening services, determine the operating systems in use, and generate a map of the network. First, let's outline how structured ethical hacking works. Ethical hacking typically has 5 phases: reconnaissance, scanning, gaining access, maintaining access, and covering tracks. Scanning, or port scanning, uses a variety of tools and techniques to dissect network resources. Let's talk about how this works. After completing a reconnaissance exercise and gathering details such as the IP address range and what data or services might be of value, the ethical hacker has more knowledge about the target. Armed with this information, the team has a better idea of how to get deeper into the system. The goal in this phase is to learn more about the network. We want to identify the type of devices that are in place. We'll also check for any defense methods that might exist, such as firewalls and intrusion detection systems. In addition, the team will check for listening services, determine the operating systems, and monitor for evidence of data being sent in clear text. Prior to starting, the team will outline a plan that includes how and what network devices to scan. The process begins by attempting to connect with listening hosts on the network. We then check for open TCP and UDP ports on a system and continue by building a logical topology or layout of the network. Scanning techniques can vary, but there are some common scans, each having a different objective. Ping sweeps send a succession of probe packets to an IP range on a network, with the goal of identifying which hosts are alive and responding. Port scanning identifies listening TCP and UDP ports on a system, with the goal of identifying the services that are active on the target. Operating system fingerprinting determines the target's operating system based on response behavior. And network mapping identifies the logical topology and creates a map. Now let's test your knowledge. Discuss how scanning helps discover responding hosts, check for listening services, determine the operating systems in use, and generate a map as flags that helps to tell the story of the data transaction. In this segment, we'll learn how TCP flags can be used when scanning to get a response, avoid detection, or determine the presence of a firewall. First, let's compare how the two predominant transport layer protocols, TCP and UDP, are used during scanning. UDP is a connectionless protocol based on speed. The UDP header only has 4 fields and no flags to manipulate. When using UDP, you'll never get a response from the host. Instead, a response from a UDP probe might be an ICMP Type 3 Code 3 port unreachable, or if the network is blocking ICMP, no message will be returned. Because of the limited response we get when using UDP when scanning, we mostly focus on TCP. The reason is that TCP has many more opportunities to manipulate the header than UDP. TCP is a connection-oriented protocol that establishes a connection to the remote host via a 3-way handshake. A TCP header contains 11 fields, which includes a 1-byte field that holds the flags. Let's talk about each of the flags and their function. Now, the first group of flags are not used during scanning, and those include reserved. Now, this is for future use and should be set to 0. Explicit congestion notification, congestion window reduced, and ECN echo are used during congestion control. Urgent indicates that this packet should have priority, and this is rarely seen. Now, the next grouping of flags are what you'll commonly use when scanning. The ACK flag acknowledges that the packets have been received. All packets after the initial SYN packet sent by the client should have this flag set. Push informs TCP that data should be sent immediately. Many times, push is used with fin. Reset is designed to allow a station to abort the TCP connection. Now, this can happen for a number of reasons, such as sensing an abnormal connection. The SYN flag will synchronize the sequence number. Only the first packet sent from each end should have this flag set, and that would be the first 2 packets of the handshake. Fin means the process is complete and there's no more data from the sender. Now, most scanners use the TCP flags. For example, Nmap can use the following techniques. A full connect scan completes the handshake and is the most reliable scan. Now, this works with most systems, but it's also the most obvious. Open ports will respond with a SYN ACK, whereas closed ports will respond with a reset. SYN stealth scan is a half-open scan, as the connection is never established. Now, this works with most systems as well and has the same responses as the full connect. A fin scan can send a fin packet to the target port. Fin packets can sneak through undetected. Now, closed ports should send back a reset. Now, a Windows machine will send resets regardless of the port state. So, a Windows machine really isn't susceptible to this type of scan. With a null scan, no flags are set, and closed ports should return a reset. An ACK scan sends ACKs, and if a reset is returned, this gives the attacker data on whether or not there's a firewall present. For example, an ICMP destination unreachable response will indicate that the port is most likely filtered. And a Christmas tree scan means that the packet is lit like a Christmas tree. And this one has the fin, urge, and push flags set. Now let's test your knowledge. Outline how the TCP flags can be used when scanning the network. TCP is a connection-oriented process, and several network scans use part of the handshake and termination process to get responses from a host. In this segment, we'll step through a TCP handshake and termination and identify the flags that are set during this process. First, let's talk about a normal TCP session. To begin, host A will send a synchronization or SYN packet to host B. The SYN packet is used to synchronize sequence numbers. If host B accepts, it responds with a synchronization acknowledgement. Host A then responds with an acknowledgement. Next, a socket on both ends is created, which is an IP address and a port, and the session begins, and both sides can then exchange data. Normally, everything goes well. However, periodically, when beginning a session, services will be refused. For example, no password was sent, so the connection is reset. No response might indicate a firewall. Or you might receive an ICMP destination unreachable packet. The code might indicate that the network was unreachable or the host was unreachable, but most likely the target port is firewalled. At that point, the host may try again with another SYN packet. At the end of a conversation, generally, there's a proper termination with an exchange of FIN packets. And you'll see the following. You'll see an ACK and a FIN, an ACK and a FIN, or you might see this combination. But sometimes the connection will simply time out and close. Now I'd like to show you an example of a TCP handshake and FIN exchange between a client and a server. If you'd like to follow along, get the file TCP start and end found in the exercise folder and open the file in Wireshark. We'll first look at the three-way handshake. Now the three-way handshake begins by going to frame 1. And here we see that the client at 10.0.0.148 initiates contact with the server at 178.255.83.1. Now, in this case, I'm going to open the TCP header and I'll scroll down so we can take a look at the flags. And here we see that the SYN flag is set. Now we'll go to frame 2. And at this point, the server then responds to the client with a SYN ACK. Again, looking at the flags, we see the acknowledgement flag is set along with the SYN flag. Then in frame 3, the client will return a final acknowledgement. And going down to the flags, we see that the acknowledgement flag is set. Now keep in mind, no data is exchanged during this time. It's just a handshake. However, once the final acknowledgement is set, the two endpoints can begin to send data. Now, TCP starts with a three-way handshake. At the end, we'll have a teardown with an exchange of FIN packets. I'll go down to frame 7, and that's where the session terminates. Here we see in this case, it's sending a FIN and an ACK. So you see the FIN flag set along with the acknowledgement flag set, and the same happens in frame 8. And then in frame 9 and 10, both sides send a final acknowledgement. At that point, the session will complete. Now let's test your knowledge. Step through the TCP handshake. Today, there are many tools available to identify devices, services, operating systems, and vulnerabilities on a network. In this segment, we'll discuss some general functions of scanners and outline a few apps used to audit the network. First, let's discuss the various functions found in scanners and what you might do when scanning the network. Typically, network scanning begins with host discovery, which identifies active devices on a network. This is done by sending probes to a range of IP addresses to see which hosts will respond. Some common methods for host discovery includes ICMP echo requests or ping scans, TCP ACK or SYN packets, and ARP requests. After the team identifies the listening hosts, the next step is to run a port scan. This determines which port on a device are open, closed, or filtered. Methods include the SYN scan, full connect scan, and the ACK scan. Beyond identifying services on a host, the team often conducts scans to determine the operating system of the target. This is achieved using a method known as fingerprinting, which estimates the operating system based on the analysis of responses from the host. For instance, consider the output of a scan that indicates with 99% accuracy that the operating system is Windows 10. Finally, upon completing all scans, the scanner can identify the topology and construct a logical map of the network. Next, let's talk about some of the tools you might use when scanning. If you do a keyword search on apps to scan the network, you'll find a wide variety of tools that are either free or for pay, and some are built into Kali Linux. Apps include the Angry IP Scanner. This is a freely available scanner for Linux, Windows, and Mac OS. Nessus is a widely used vulnerability scanner that's commercially available but free for personal use. AirCrackNG is a suite of tools for wireless LAN auditing. OpenVAS is an open-source vulnerability scanner, and Nmap is another open-source tool for network discovery and vulnerability scanning. Unicorn Scan comes pre-installed with Kali Linux and is a fast, efficient scanner. Let's take a look. I'm here at this page where we can learn more about the key features of Unicorn Scan. I'll scroll down. One key difference is that Unicorn Scan uses asynchronous scanning, where instead of waiting for each scan to finish, each scan is started independently and can run simultaneously, which results in faster responses. However, you will need a device with enough muscle to handle the resources required for this type of scanning. In addition, the team may be tasked with scanning mobile devices. There are also a wide range of tools available. Drozer is an application security testing framework that's specifically designed for Android devices. Quark Engine is an open-source Android and iOS malware scoring system. Mobile Security Framework is an automated app used to test Android, iOS, and Windows systems. And Fing can help you troubleshoot your network. I'm here at Fing's homepage, where if we scroll down, we can see how Fing can show you what's happening on your network. Now let's test your knowledge. Nmap is a powerful and flexible open-source network discovery tool. In this segment, we'll outline some of the Nmap scans available that include host discovery, port scanning, and operating system detection, along with some additional features to help streamline your scans. Once you understand the basics of scanning, you'll want to evaluate some of the tools that are available. One of the more popular scanning tools is Nmap. Nmap, or Network Mapper, provides a wide range of scans and options. In addition to standard scans, Nmap has a wide range of features to optimize scanning on any size network. Let's take a look. I'm here at nmap.org, where we can see the online version of the Nmap book. Once here, you can read about all the available techniques that include finding live hosts and listening services. I'll scroll down, where you can read more about host discovery or ping scanning, learn all the methods available for port scanning, along with diving into ways to perform operating system detection. One thing to keep in mind is that Nmap is highly efficient. However, there are times when scans take a lot longer and they will generate a lot of traffic. This is common when scanning a large, complex network. It's possible to reduce Nmap scan times, and the guide lists several methods. I'll go to Chapter 6, and I've opened it in a new tab, where we'll find multiple methods to optimize scanning. Methods include the following. Omit non-critical tests. For example, disable DNS resolution and scan only 100 ports instead of the default 1,000 ports. Optimize timing parameters. For example, slow the rate of probes per second. Or we can increase available bandwidth and CPU time. I encourage you to check out this valuable resource where you'll find plenty of scanning information and examples within the book. Now let's test your knowledge. Outline some of the Nmap scans available that include host discovery, port scanning. HPing3 is a command line tool that can create specially crafted packets to send to a remote host. In this segment, we'll learn how we can use HPing3 to scan, spoof, or launch an attack. HPing3 is very flexible, and depending on your objective, specific flags and options can be set. The tool can craft and send ICMP, UDP, or TCP packets to a remote host and print the results. It can be used to spoof a source address and determine firewall rules with the goal of evading the firewall. HPing3 can also be used as a backdoor to create a shell that redirects the output and input to a service so it can be accessed remotely. And it can also be used to launch an attack. With HPing3, we can do standard scans, such as a ping sweep, SYN-scan, or a Christmas tree scan. We can specify IP options, such as randomize IP source and destination address, along with other options, such as timing intervals and setting specific flags. Let's jump into Kali and see how this works. I've opened up a terminal so we can do a simple ping scan using HPing3. I'm going to ping scanme.nmap.org, which is a site that allows you to test and do some pinging and scanning. So I've entered the command, and I'll press enter. And I'll stop that. Okay, so you can see that's a simple ping scan. But what is truly neat about this tool is that it allows you to spoof your source address, and it will throw a bunch of random source IP addresses during an attack. Let's talk about how I can use this feature. A SYN flood is a denial of service attack that floods a server with bogus SYN requests with the goal of locking out legitimate users. To improve the effectiveness of the attack, it should appear as if the packets are coming from multiple sources. That way, security devices are unable to tell where the attack is coming from and whether the requests are legitimate or not. So to launch a denial of service attack and use a bunch of random IP addresses, I'll go into HPing3 and run a SYN scan using the random source mode. And here we see the command. Now, so we can see the random IP addresses that HPing3 generates, I'll launch Wireshark here within Kali and start the capture. So we're going to move this over and I'll launch Wireshark. I'm going to start the capture, and I'll minimize this, and now I'll begin the attack. Now I'll stop the attack, and I'll go back into Wireshark. I'll stop the capture, and now what I'm going to do, you probably can see some of the IP addresses, but I'll filter by TCP, and now you'll really be able to see the random source IP addresses. Now, because I used the random source mode, we see a bunch of bogus IP addresses that are pretty much all over the map. Now, with a denial of service attack, the idea is to throw multiple IP addresses at the host, so they really have no idea where the attack is coming from and whether the requests are legitimate or not. Now, I'll minimize this, and I'm at the man page for HPing3. Once there, you can check out all the options that you can use when using HPing3. Now let's test your